Well, this is not going to be a talk on low-dimensional topology, and it's not directly Kirby's work, so you might wonder why it fits in here. I thought it would be interesting, though, to have a sort of warm-up talk showing what topology was like from the perspective of someone beginning research in the mid-60s. I see several people in the audience who also were setting out in the mid-60s. I better apologize in advance because I'm not going to do justice to most of your work. Well, when I started research, my advisor, Terry Wall, said you should study surgery. Now, when one thinks of surgery nowadays, one probably thinks of Dane's surgery on three manifolds, say. That is a topic that was greatly popularized by Rob's link calculus. I wasn't going to talk about that. I think there'll be other talks on that. So anyway, Terry Wall said I should study surgery of high-dimensional smooth or piecewise linear manifolds. And that theory was already very well developed and went a long way towards classification of these manifolds, as I'll try and explain. Let's see, is it possible to put on the next row of lights? I used to know how to do it. Yeah, good. So surgery for smooth or piecewise linear manifolds of high dimension was a very well-developed theory in those days, in the mid-60s. It was clear, though, that what everyone wanted to do was to study topological manifolds. In those days, high-dimensional topological manifolds. So this was before 1968. The theory of topological manifolds before 1968 was a very small theory. Not really very much was known. An example of maybe almost the only result in pure topology that applied in all dimensions and was known before 1968 was the Schoenflies theorem. So this was Schoenflies' original theorem was for circles in two-dimensional manifolds. I'm thinking of the version proved by Barry Mazur and Morton Brown, I think 1960, which says that if one is given an embedding of an n-1 sphere across an interval, so it just has to be one-to-one and continuous, then the closures of the components of Sn minus the embedding of Sn minus 1 cross 0 are homeomorphic to balls. So this is, I suppose, if one were starting out naively, one might say, well, is it true that every 1-1 continuous embedding of an Sn minus 1 in Sn separates the Sn into two components, each of which has closure a ball? That was well known not to be true with the Alexander Horn sphere as an example, but that can be fixed by allowing oneself instead an embedding of Sn minus 1 across an interval, and then the middle level of that embedding is actually does separate the sphere into two components, each of which has a ball as its closure. And any two embeddings are equivalent by homeomorphisms. oh, sorry, I shouldn't say that at this point. Let's just leave it at that. So this is what was known, and an example of something that everyone knew they wanted to prove but wasn't known was the famous annulus conjecture. This was definitely a conjecture before 1968, proved by Rob Kirby, well, Kirby and Siebermann actually, in 1968. So this says that if E from, let's make it a ball, but let's make it a ball of radius 2 rather than a ball of radius 1, into the interior of a ball is, again, 1, 1 and continuous. Just point set topology here. Then the closure of the complement of that embedding, well, not the whole embedding. One has to allow oneself to cut down. This is a ball of radius 2. Let's cut down to the ball of radius 1. So, yes, sure, yes. Let's move the. I'm going to need an eraser at some point. Yeah, there we go. Then Bn, the ball minus the image of the radius 1 ball, its closure is homeomorphic to what one would expect, namely an Sn minus 1 across an interval. So we're given an embedding of a ball of radius 2. So this is E of the ball of radius 2. And it could actually be an Alexander Horn ball for all we know. So it's not realistic to expect the region between the outside ball and the embedded ball to be an annulus. But if we cut down to the image of a concentric ball, so this is the image of the concentric ball, we fix it the same way that the Mazur-Brown theorem did for the Schoenflies theorem, then it is reasonable to expect, and a lot of people did expect, that the region between the big ball and the embedding of the radius 1 ball, that's this region, would be homeomorphic to, would be the same as for the standard embedding, namely an n-1 sphere across an interval. So this is the annulus conjecture. It was proved by Kirby and Siebermann, the key ingredient being Kirby's famous torus trick, which will be the subject of another talk. But anyway, in the mid-60s, it seemed completely inaccessible. And actually, people in the mid-60s, well, certainly to me, it looked as though if this could be proved at all, it would be done by incredibly hard work, sort of maybe approximating this badly embedded ball by nicely embedded balls from the outside, and somehow using some limiting argument to say that the complement wasn't too bad. But it looked like incredibly hard work. And that is not what Rob did at all. He made a very, well, that's not the end product anyway. The end product was a very elegant and amazingly simple bridge between the categories that we knew about, the smooth and the Peace-Lausinia categories, and the unknown category, the topological category. And so this bridge was the torus trick. And it is amazingly simple and ingenious. I'm sure it did require enormous amounts of hard work to find it, but it's really not so hard to describe. And an interesting thing about it, though, is that well, actually, it can be used. It can be used in an elementary form to prove interesting results as a completely self-contained and elementary argument. I guess it uses Morton Brown's, the Maser-Brown argument, the Schoenflies theorem. It can be used in a completely elementary way, but in order to get the most out of it, in particular, in order to prove the annulus conjecture, one has to use Robb's torus trick, the bridge, and essentially everything that was known at the time about smooth and piecewise linear manifolds. These are the things that were proved by high-dimensional surgery. So I want to explain a little bit about high-dimensional surgery and what it could do. Well, I'm not going to be talking about the torus trick, but I'll try and say something that's relevant to the torus trick. So, high-dimensional surgery. Well, so suppose suppose we're given a manifold. Let that be a closed manifold of dimension n, and I'm thinking of a C infinity, a smooth or maybe piecewise linear manifold. And I'm thinking of n as being high dimensional, but it doesn't have to be here. And we're also given an embedding from a k-sphere crossed with an n minus k-sphere into M. You notice that this is a k manifold, so this embeds onto the closure of an open set, actually. An n manifold, yes. Same as on this side, yes. Yeah. Well, in the construction of surgery, what one can do is to notice that the n sphere can be decomposed into sk cross bn minus k, together with, there's another obvious piece of the n sphere that has the same boundary, namely the bk plus 1 cross sn minus k minus 1. So this is referred to often as a spherical modification. So surgery on M along E is a construction that can now always be performed, and what it yields is, let's suppose we cut out the image of this embedding, and then we attach, there's an obvious other manifold with this same boundary, namely a bk plus 1 cross sn minus k minus 1. If you look at these two pieces, I say remove this piece and reattach this piece, they both have the same boundary, namely sk minus sn minus k minus 1. So that makes sense. If we're doing this with smooth manifolds, then it's not immediately obvious that this is a smooth manifold. There's a corner that has to be rounded, but well, that's a technical nuisance. So this is the construction of high-dimensional surgery. How does it correspond to low-dimensional surgery, Dane surgery on 3 manifolds? Well, it's a generalization of a special case. So if you take the case when n is 3 and k is 1, then this corresponds to integer surgeries on circles embedded in a 3 manifold. And Dane surgery would also allow, so that actually be, for a given embedding of a circle in a 3 manifold, different choices of the framing of the torus neighborhood would give infinitely many integer surgeries corresponding to this construction, but also there's a 2-parameter infinite family of Dane surgeries. So this is a generalization of a special case of Dane surgeries. So what was this high-dimensional surgery used for? Well, the first thing, the first application was to classify. Let's make this smooth C infinity n manifolds with a homotopy type of the n sphere. and this is for n at least 5. So you notice that n equals 4 and n equals 3 for C infinity manifolds, those are unsolved to this day. So this, the starting point of this was Milner's discovery in 1956, I think it was, that on the 7 sphere there are many, in fact 28 differentiable structures. So the theorem, and this is due to Kerver and Milner, 1960, I think it was published in 63, but it was probably done quite a bit earlier than that. If we consider C infinity manifolds homotopy equivalent to the n sphere, they form so diffeomorphism classes of C infinity manifolds homotopy equivalent to the n sphere form a finite abelian group with connected sum as the operation. And a lot of this is easy to prove. It's not so easy. So it's easy to start with a class of homotopy n spheres and the connected sum operation try and make that as a group operation. And you get an abelian group. You get an abelian monoid anyway. To get inverses, well, it's not so clear that you get inverses if you take the classifying relation as diffeomorphism. H-cobordism is the natural relation that you would come up with. So there's work involved in showing that this is actually a diffeomorphism classification, but that smells H-cobordism theorem. The key thing that Kerver and Milner did was to show that this is a finite abelian group, and they showed how to say how big it is. And so I want to explain how surgery was relevant to this. So this is topology as seen from the mid-60s. So it was different then. So here are the steps. So given M, homotopy equivalent to an n sphere. So the step 1 is to show that the tangent bundle of M, I guess it's not. This is not so essential, but this is the way it was classically done. So let's do it this way. The tangent bundle of M, well stabilized by crossing an interval, is trivial. So this was done by. This is a piece of algebraic topology based on work of Frank Adams. So this is something in the nature of a preliminary. So it was known at that stage that any homotopy n sphere had a trivial, well, not necessarily a trivial tangent bundle, but it became trivial after stabilizing once. So it could be considered to represent an element of the framed Bordism group. Which can be represented very concretely as the pi n plus k of the k-sphere, where k is large. And the way this happens is that, this given manifold M is realized as the preimage of a point under a map from Sn plus k to Sk, the map being transverse to the point that we take the preimage of. And that's something you can do only if the tangent bundle is stably trivial. Well, the nice thing about this is that this was known to be a finite group, finite abelian. So that was progress. Then the next thing is, sorry? Yes, yes. This is going to be, yeah, that's perfectly true. So from the tangent bundle being trivial, what one actually needs to completely determine this class, one needs to choose the trivialization. Yes. You're going to see many instances of. Sorry, I'm not going to get this. Well, let's work on number 2. So since this is a finite abelian group, there's a good chance, if we're lucky, there's a non-zero chance anyway, that our manifold will represent 0 in that group. So we're trying to prove that we have a finite group here, so that's okay. Then, well, that means that M is the boundary. M is an n manifold, W is an n plus 1 manifold, where W is compact with trivial tangent bundle. Turns out that you get that W has trivial tangent bundle. Now, what we'd really like is for W not to be just compact with trivial tangent bundle. We'd like for W to be contractible. So let's write that down here. If W is contractible, which it probably isn't, then Smale, 1961, essentially his H-cobordism theorem, implies that that W is actually, and we're using that n plus 1 is at least 6 here, that W is actually diffeomorphic to the ball, and in particular, M being the boundary of W is diffeomorphic to the sphere. So that's what we'd like. We'd like for W to be contractible. Unfortunately, we don't know that at all. We know that it has trivial tangent bundle, and that's about the only help we have. So let's go to another board here, because this is where surgery comes in. So we have this manifold W, whose boundary is the given manifold M, and we'd like W to be contractible, but it probably isn't. So we use surgery to kill the homotopy groups of W, starting at pi 0, which is probably might as well have W connected to begin with, then pi 1 and pi 2, I guess, and we keep going until it becomes difficult. So let's not commit ourselves to where it becomes difficult right now. Surgery in the 60s was only used for destructive purposes. So pi 0 isn't interesting, but pi 1, for instance, if W, we'd like W to be simply connected, it might not be though, so choose some element in pi 1 of W and represent it by a mapped-in circle initially. It's easy by general position. We're safely below half the dimension of the manifold. Well, I didn't say how far I was going to go, but let's we better not go too close to half the dimension of the manifold. Then by general position, we will always be able to get this to be an embedding of Sk in Mn. Oh, M is now Wn plus 1. Sorry about that. And the manifold in which we're embedding has trivial tangent bundle, and from that, it's not hard to show that the embedding of the circle will have trivial normal bundle. And so you get the ingredients for surgery, do the surgery, and the Sk, in this case S1 that I was describing, then seems to, or a little parallel one, seems to bound a ball. So that means that we have actually killed off its homotopy class. It's now null homotopic in the new manifold. You might worry that we've also introduced a meridian. So this circle embedding in Mn has a meridian, which I guess is an Fn minus k minus 1. Well, I propose to keep k well below half of n, and so this will be higher dimensional, and so it's not something we need to worry about at this stage. So you you look and see how far you can be absolutely sure that this will work. And I think the answer is n plus 1 over 2 minus 1 of W. Stop 1 below halfway up. And that always can be done. So just by using this surgery construction, there are a few technical details, but it's basically not hard. One can actually make sure that all the homotopy groups of W has the desired manifold, the manifold we're interested in as boundary. We'd like W to be contractible. We can get all the homotopy groups up to one less than the middle to be trivial by using the surgery construction. If we could kill the next one, then so that's going to be hard, but if we can do it, then we don't have to worry anymore. Poincare duality comes to our rescue. It turns out that all the higher homotopy groups are automatically, they're dual to ones we've already killed. And Poincare duality so the whole art in applying this surgery technique, and this is what Cavera and Milner worked out here, is to decide whether it is possible to kill this first difficult dimension, which turns out to be the last one that you need to. So the next thing is to kill pi n plus 1 over 2 of W if you can. It always works. So this is not easy, but it's easy to state. If n is odd, sorry, n plus 1 is odd, it's the dimension of W that's the important thing. So I better remind you that W is an n plus 1 manifold here. If n plus 1 again, is congruent to 0 mod 4, we can do it if and only if there's an obstruction which is the signature W is now a manifold of dimension 4k for some k, and so it has a well-defined signature, and it's easy to see that that signature is an obstruction, and it turns out to be the obstruction to carrying out, to killing this remaining homotopy group. And n plus 1 congruent to 2 mod 4, we can finish it off. If a certain ARF invariant so I will not attempt to tell you about ARF invariants. There's something like a quadratic form which has something like a signature, but is actually an ARF invariant, and it takes values in mod 2, in Z mod 2. So if the dimension of our homotopy sphere is congruent, well, if n is the dimension of the homotopy sphere and n plus 1 is divisible by 4, then there's an integer obstruction which can be thought of as a signature. If n plus 1 is congruent to 2 mod 4, there's a Z mod 2 obstruction which arises as this ARF invariant of a suitably defined quadratic form. So if these obstructions vanish, we get that in fact W is a ball, and so we get that M is Sn minus 1. Oh yes, so I have. M is an n manifold. Yeah, I couldn't decide whether to use, well, how to index them. Oh, I dropped it over here too. That's it, yeah. So this is the systematic use of surgery to prove an interesting theorem here. Incidentally, there's an interesting little example. Well, it's an important example. Oh, yeah, there's one thing. It might, since there's an integer signature, that might seem to open the door for the group we're studying to be an infinite group. It turns out, though, that there is an n+1 manifold with non-zero signature, but which has the n sphere, has the standard n sphere as boundary in all cases, and so this gives rise to a cyclic group, but it turns out to be a finite cyclic group always. There's an interesting manifold associated with this, namely, so the signature of such a manifold is always divisible by 8 for number theoretic reasons. And so it's of interest to know an example of a 4K manifold where the signature is as small as it could be, namely 8, non-zero and as small as it could be. And so that actually generalizes this well-known example in dimension 3, or dimension 4 rather. So if we take the Kirby diagram, so this is a link surgery diagram, and so this, a lot of people will recognize that as a picture of the Poincare homology 3-sphere. So this has generalizations in high dimensions in any. So actually, thinking of this as a Kirby diagram, realizes the Poincare homology 3-sphere as the boundary of a 4-manifold, the 4-manifold having, in fact, signature 8. And so this generalizes to construct 4K dimensional manifolds. And the boundaries actually are not just homology spheres, but they're homotopy spheres if the dimension is bigger than 4. So this is very successful for classifying manifolds with the homotopy types of spheres, and it doesn't stop there. Classify manifolds, let's make it n manifolds, homotopy equivalent to a given closed manifold n of dimension capital N. And again, I want little n to be at least 5. This is high dimensional. These things just, you can try and make these things work in lower dimensions, but well, it's been tried a lot, and some of it has been made to work and some doesn't, apparently. And let's also have capital N simply connected. Well, so what do we want to do? We want to classify them up to, let's make them C infinity at this point. We want to classify them up to diffeomorphisms. So this is the set whose members are going to be, roughly speaking, C infinity structures on a given manifold. So S sub diff I will write as a notation of n. So what I said wasn't quite right. I want to classify C infinity structures on manifolds homotopy equivalent to the given manifold capital N. And in order to be sure that my manifold is homotopy equivalent to capital N, I better provide an explicit homotopy equivalence so you can check that it is. So this set, the set of homotopy C infinity structures on N, you could say, is, so what we're actually classifying are pairs M, H, where Mn is a closed C infinity manifold, and H from M to N, that's the N that occurs over here, is a homotopy equivalence. So the kind of thing that we'd like to classify, so we're given the manifold n is given to us, what we'd like to classify is, are all possible C infinity manifolds M equipped with homotopy equivalences from M to the given manifold N. And the equivalence relation will be, well, in order to regard, so suppose we have two of these, M1 given with a homotopy equivalence, I don't need to write N twice, M1 given with a homotopy equivalence H1 to N, and M2 given with a homotopy equivalence H2 to N. A first requirement would be, in order to regard these as equivalent, we should certainly have M1 and M2 diffeomorphic. But since we've built in to the setup the given homotopy equivalence, we should actually require that this be a diffeomorphism in the right homotopy class. So it should make, so the diffeomorphism followed by H2 should be homotopic to H1. So this should be homotopy commutative diagrams of that form. So this is the thing that we actually want to study. So, well, let me. I say the time is. I'm obviously not going to cover everything that I hope to cover. It turns out that this argument that was given for spheres can actually be generalized to this setting. So let me jump to to sum up the conclusion. So this in the 60s, geometric topology resembled algebraic topology much more than it does now. And so the typical way to present the result is in terms of an exact sequence. So the set that we're interested in, S diff of n, homotopy smooth structures on n, fits into the middle of an exact sequence. And the term over here, I'll need to explain what some of these things mean. Let's just write down G over O at this point, and I'll tell you what it is. And then the extreme term on the right is L sub n. I'll tell you what that is also. And then this is the kind of exact sequence that you see in algebraic topology. So you guess then that this one over here would be Ln plus 1. And the next one along would be what? This G over O is some space, and this is the set of homotopy classes of maps of n into that space, G over O. And so the next thing you get on the left with the same thing, but with the suspension of the space instead of the space. And it can be continued further, but let's stop there. So if we, so this is the surgery exact sequence. I should be saying who these things are due to. The idea of generalizing surgery to classify manifolds that are not necessarily homotopy equivalent to spheres, but homotopy equivalent to some manifold, I think that's due to Novikov and Browder. And then expressing it in this succinct form, I think is due to Dennis Sullivan, if I remember right. He called this F over PL, but well, it's not quite the same, but we'll come to that. So what are these things? Let's call this map eta sub n. This is the set consisting of the structures on manifolds homotopy equivalent to n that we'd like to analyze, and passing to the corresponding to the image in this set, that's taking its normal invariant. So this map means take the normal invariant. That's just terminology, it's not really telling you anything about it. And this is the surgery obstruction group. So what is G over O? Let's see if I can explain very briefly what that is. G over O, well, I'll tell you what G sub k over O sub k is, and then G over O is actually the limit as k tends to infinity. O sub k is a topological group, so the notation suggests that G sub k is a bigger topological group, and this is just the orbit space. That's a hard way of approaching this, I think. The thing is that if one were to try and make G sub k into a topological group, what would it be? Well, we're comparing smooth structures which correspond to which have vector bundles corresponding to the group O sub k with homotopy information, and so this will be the group of self-homotopy equivalences of a sphere, except that it's not a group. So O sub k is contained in this monoid that's not a group, so it's not so clear what the orbit space is. So what this does is the classifying space for k vector bundles equipped with fiber homotopy trivializations So that sounds very complicated. What does it mean? If you have a k vector bundle, then you can always take an associated k-1 sphere bundle. And so you ask that a fiber homotopy trivialization says that sphere bundle resembles the trivial bundle as far as homotopy goes. So it would be sufficient, actually. If you want to know whether a given k-vector bundle is fiber homotopy trivial, it would be enough to ask for a commutative diagram from the total space of the sphere bundle to the trivial bundle, the base space across the sphere. That should be refined a bit to get a good theory, but this is a theory that has a classifying space, and this is it. So let's see what. I'll finish fairly soon. Let's see if I can say a few words that indicate why this might work. So we have some. This is a very much stripped down exposition. So we have some manifold. Let's consider an element in our structure set. So we're given a pair consisting of a smooth manifold, a C-infinity manifold M, a given manifold N, and a homotopy equivalence to the given manifold N. Then let's consider N cross Rk with K large. And that's going to be, think of that as a trivial bundle over N. Then one thing we can always do is to take a homotopy equivalence and deform it to a smooth embedding. I'm cheating a little bit here. I want to regard this as a smooth manifold, and so that requires N to be a smooth manifold. I didn't say that it was, but better expositions wouldn't require that. Anyway, let's deform this to be a smooth embedding homotopic to H. And then it will have some normal bundle. So let that normal bundle be smooth maps. Smooth embeddings always have normal bundles. So let the normal bundle be Xi, so it has some total space. And so that smooth embedding then extends to a smooth embedding of the normal bundle. And so a little bit of thinking about it shows that you can actually, so here's a picture of N cross R, very schematic picture of N cross R. And so we've taken this homotopy equivalence with N, so this is now M in here, and we've got a smooth embedding of its normal bundle. And so, this embedded normal bundle is a deformation retract. So if one stares at that, one can actually see that it's not too hard to see that this normal bundle has to be fiber homotopically trivial just by comparing with what's outside. And you can actually see a fiber homotopy trivialization. So you adjust this to make this a fiber homotopy trivialization. And so that is the associated normal invariant. And now, suppose now we're given an element of in the set n g over O, so think of it as a vector bundle over n and a fiber homotopy trivialization of it. So here's the vector bundle. I'm putting the fiber homotopy trivialization the other way, I think. So here's the vector bundle, C over n, and here's its fiber homotopy trivialization. So let's call that capital F. And again, I'm cheating by assuming that n was a smooth manifold to start with, but we can make this transverse regular to the zero section. And if we do that, then, as is well known, the inverse image will be a smooth manifold of dimension, or codimension k, so it'll be a smooth n manifold again. And we'll have a map this way. Now, what we would like is, so we want this to be a homotopy equivalence. But it probably isn't. If it were a homotopy equivalence, then we'd be back in this setting, and we would actually have shown that our potential normal invariant, n, a map from n to g over O, really is the normal invariant of some pair, namely m and this map here, this homotopy equivalence here. But if you just do this construction carelessly by transversality, well, then you probably don't get a homotopy equivalence here. So how do we make it into a homotopy equivalence? Well, do surgery. And it turns out that all the condition, it's amazing that this works, at surgery, so try to promote to a homotopy equivalence by surgery. And it turns out that the theory is almost exactly the same as what I described here. You can, but when we do surgery, we don't want to kill all the homotopy groups of M. That wouldn't be the right thing to do. What we want to do is to kill the relative homotopy groups of the pair. Well, the easiest pair to name here is n cross Rk and the subspace M. To kill the homotopy groups of the pair n cross Rk, comma M. And again, it turns out that one can go almost as far as one needs to go, essentially for free. So it's amazing that it works, but it does. And there's just one remaining case, the so-called middle dimensional case, where one runs into potential obstructions, and the obstructions are just exactly the same as they were in this setting. So there's a potential Z obstruction if the dimension, it's n this time, is congruent to 0 mod 4, and there's a Z2 potential obstruction if n is congruent to 2 mod 4, and otherwise the surgery can always be done. So that fits in with this long exact sequence. So Ln is the surgery obstruction group in dimension n. And so what it is, well, it's just, so it's Z if n is congruent to 0 mod 4, a group to contain the signature of a quadratic form. It's Z mod 2 if n is congruent to 2 mod 4, and it's 0 otherwise. And then the same rule goes for Ln plus 1. So there, very broadly, I've described the surgery exact sequence. And let's give a name to the map. I don't know that I'll ever get down to using this, but let's give a name to this map. In a very stripped down version, I told you how to take an element of this set and convert it into a surgery problem, and theta n is its abstraction, the signature or half invariant or whatever. Well, let's see. So this really could be made to work to give a very good hold on the classification problem for up to diffeomorphism of smooth manifolds homotopy equivalent to a given manifold. Well, I'm just erasing I haven't quite erased all of the Ennius conjecture yet. And I mentioned that required just about everything that was known at this point. So I better start summarizing rather rapidly what was needed. This I've described for differentiable manifolds, for C-infinity manifolds. Now, as I mentioned earlier, people, topologists at that time, well, they liked differential manifolds, sort of mainstream mathematics. But on the other hand, what they really wanted to do was to study topological manifolds. And they had the feeling that, which turned out to be quite correct, that piecewise linear manifolds are much closer to topological manifolds than differentiable manifolds are. Piecewise linear manifold is, well, it can be defined, a compact piecewise linear manifold is one that can be triangulated so the link of each vertex is combinatorially standard, has a subdivision isomorphic to a linear subdivision of say the boundary of a standard sphere. Or piecewise linear manifolds can be defined in terms of charts, where the overlap functions, the transition functions are linear on simplices of some subdivision. So it's a rather more complicated theory to set up. Well, in some ways simpler. Anyway, so there's a surgery exact sequence for piecewise linear manifolds. So let's take a piecewise linear manifold n, and again n will have to be at least 5, and for the moment let's have pi 1 of n trivial. So this exact sequence, well, it's easy enough to say what the structure set for piecewise linear structures on manifolds homotopy equivalent to n should be, so let's just suppose that's said. Now we have to build this space that receives the normal invariant. So there's a normal invariant which can be defined in a similar sort of way, and it takes values in a space, an even more obscure space to define, G over PL. Dennis Sullivan called it F over PL, but anyway, same space, I think. So actually, the main difficulty in generalizing, in doing surgery theory for piecewise linear manifolds as opposed to smooth manifolds, is one needs a theory of normal bundles. So for smooth manifolds, every smooth submanifold of a smooth manifold has a normal bundle. It's not clear to begin with what that means for piecewise linear manifolds. So that's something that had to be sorted out. That was really the main new thing required. And so when one sorted that out, this is the classifying space for piecewise linear bundles equipped with fiber homotopy trivializations. And it turns out that the surgery abstraction groups are exactly the same. It doesn't make any difference at all. And so you get, am I using S for suspension? So I haven't really told you at all how to make this space G over PL, even less than I did for the smooth manifold. But I can tell you, following Dennis Sullivan, quite a lot about it. Well, I'm only going to scratch the surface, of course. So I can tell you, for instance, what the homotopy groups of G over PL are. So this is a space, G over PL is made by a very sort of abstract classifying space. A priori, very little is obvious about it. But we can feed it into this exact sequence, and with one other ingredient, we can read off what the homotopy groups of G over PL are, even though we have a very hazy idea of what G over PL of a space might look like. So the way to do that is to set N as, that's the given manifold, as a sphere. So we need an input here. So this is a theorem due to John Stelling's. Let's see. Well, I think I should be, well, we're very sketchy in attributions all around. So there's a theorem due to John Stelling's that proved using engulfing techniques, so a bit different from what I'm describing, that Fn for n at least 5 has a unique piecewise linear structure. So in the convergence theory, that was for smooth manifolds. Well, Miller already showed that that wasn't true for smooth structures, but it is true for piecewise linear structures. Again, it's not known what happens for 3 or 4. Oh, sorry. Well, it's not known what happens for 4. Other things are not known for 3. Well, yes, I was wondering. Yeah.
If you don't mention demon, what's food?
Yes. Sorry, I'm not being systematic about attributions at all. So let's see. Yes, you're probably right. Yes, okay. Yes, okay. Well, we'll talk about that later. I'm not convinced, but never mind. Let's see exact sequence. So set n equal to the n sphere, and see what we get. These are supposed to be called theta sub n, and this is theta sub n plus 1. So if provided dimensions at least 5, this is the trivial set. Oh, you might have wondered what I mean by an exact sequence when this isn't a group. Well, there's a way of making sense of that. Don't worry about it. So the conclusion is that this is actually a long exact sequence. The conclusion is that these maps theta sub n are all isomorphisms. Theta n goes from homotopy classes of maps from Sn is G over PL, that's pi n of G over PL, to these third obstruction groups, Ln, that I wrote down, and that's an isomorphism. However, look in quite all dimensions. It works if n is at least, let's see, to get this one onto, we better have n at least 6 probably. And LNR, I wrote them out, they're simple. There's V in dimensions congruent to 0 mod 4, Z2 in dimensions congruent to 2 mod 4, and trivial otherwise. So we can write on all the homotopy groups. Yeah, I've got to stop, haven't I? I've got to stop in about 1 minute. We can write down all the homotopy groups of this space G over PL that that receives the normal invariance of piecewise linear manifolds. So we're getting close now, and we're not there, but we're getting reasonably close to the point where we can prove something that's useful to Rob Kirby for the annulus, purposes of proving the annulus conjecture. So for the end, I think I just have to. We need the following part. Through these techniques. So this is a theorem that, so if we look at piecewise linear structures on the n torus, doesn't quite fit into what I'm saying. The reason the end of the torus, that's the Cartesian product of n circles, is not simply connected. I want to have n at least 5, so it'll be higher, but it's not simply connected. Its fundamental group is v to the n, so that's different. So we have to generally accommodate non-connected manifolds. It turns out for third groups that have to be generalized now, but they're much more complicated. But the state of the art in those days could handle that. Principally, work of Terry Wall made a systematic foundation for connected surgery. And the right finite this was linear structures on the end of the torus, and they were naturally indexed by elements of the third homology of the torus with z natural coefficients. So we know to count those n 3 or whatever. That's the number of homotopy structure of PL on manifold homotopy equivalent to the n-dimensional torus. And so that's what was needed for the resolution of the conjecture, and very fortunately it was just where topology had reached in those days.